Thank you very much. In fact, I've never used one of these, and I like to speak with my hands. So if I start waving, then you should warn me, because then probably you won't hear me anymore. So thanks a lot to the organizers for inviting me. In fact, the organizers gave me a slightly daunting task of reviewing all of thermodynamic cosmology in just an hour. And so that's almost impossible, I found when I tried to prepare this. So what I had to do is make a couple of very personal choices, okay? And so I want to warn you from the beginning that the kind of things that are selected aren't universally, the truth, or, well, I hope they're true, but I chose them with some kind of bias as I had. Okay, but we'll see how it goes. So this is my plan. So what I want to do first is I want to give you a very broad outline of what I consider to be the central goals of early universe cosmology. So I like to call this the cosmological inverse problem. And that's basically the problem of how we relate observations that we make at late times and low energies to more fundamental information about time and behavior of the theory. And I thought, so since most of you probably are interested in the UV, I think it's still useful to understand in a little bit of detail how we make that connection, just so that you see where the limitations are. Okay, what kind of things you can hope to learn from cosmological observations, and what limits us. That's going to be rather broad and general, and so then I want to focus more specifically on two applications. In particular, I want to discuss the non-Gaussianity of the fluctuations and how that can teach us something. And then finally, I also say something about tensor modes and how tensor modes are sensitive to UV physics. And then finally, I'm going to end with some very brief comments about future observations. Okay, so let me start describing to you what the cosmological inverse problem is. So as I said, that's the problem of how we go from late-time observables, and those are mostly observables of the fluctuations in the cosmic microwave background, but also fluctuations of the large-scale structure of the universe, and how these fluctuations grow in time. And so the central challenge is how we take these observations that we make at late times and infer something about the cosmology of perturbations. Okay? So that's the first link we have to establish. And then more ambitiously, we also like to explain where the cosmology of perturbations came from. So what their fundamental or ultraviolet origin is. So very schematically, that's the central goal of this type of research. But of course, a lot of work, entire research areas are contained in these errors. There are decades of work literally trying to make these things precise. Thousands of papers trying to make these things precise. So I thought it would be useful to unpack this kind of picture a little bit. So that's what I want to do first. So let me first explain a little bit how we make this link between observations we make at late times and the primordial origin of these fluctuations. So as I already said, the key cosmological observable is the cosmic microwave background. That's the cleanest probe we have of fluctuations in the early universe. So the early universe was still very linear at the time when the CMB was formed, and that's why it's a very pristine picture of the fluctuations at that time. So about 380,000 years after the Big Bang, this afterglow of the Big Bang was formed. And so we see it today, and we see it varying across the sky. And of course, you see here this beautiful image of a map of the sky and showing the temperature of the microwave background as a function of position in the sky. Okay? So these are 10 to the minus 4, 10 to the minus 5 variations on top of a mean black body segment. We can take correlation functions of that map. So in particular, we can take a 2-point correlation function. That 2-point correlation function that you see here is made out of about 10 to the 6 data points. And so it's rather remarkable that these 10 to the 6 data points are fitted by just 6 parameters. Okay? So this red curve here varies according to cosmological parameters. There's 6 of them. 4 of these parameters describe the composition and geometry of the universe. 2 parameters describe the initial conditions. But those 6 parameters are sufficient to fit these 10 to the 6 data points. Okay? So it's a highly constrained curve, and this curve didn't have to fit, but it seems to be working at this degree of accuracy. Okay, so then the next step in the problem is to take these fluctuations that we observe at recombination and trace them back in time. And here we want to trace them back to the beginning of the hot Big Bang. Okay. And so here by the beginning of the hot Big Bang, I simply mean a time that was sufficiently early that all of the modes of interest that we observe in the microwave background were outside of the horizon. Okay. And we know that once the modes were outside of the horizon, they were frozen and constant. So it doesn't really matter when we pick this time as long as it was sufficiently early during this Hot Big Bang phase. So at that time, we can identify perturbations in the curvature, spatial curvature of the universe. These curvature perturbations are co-moving curvature perturbations. We call them zeta as a function of position x. We can measure the two-point correlation function of these curvature perturbations. And so what we find is that the power spectrum or two-point correlation function of zeta is very nearly scale invariant. Okay? So it has an amplitude that has been measured a long time ago in 1992 by Kobe, which is the same as 10 to the minus 5 squared. But importantly, it also has a slight deviation from scale invariance, which was discovered only recently. In fact, I should have also cited WMAP, which was the first to really establish a significant deviation from scale invariance. And then Planck now has made this very significant, so this is now a, I think, 7 sigma detection of a deviation from a perfectly scale invariant spectrum. So that's what these fluctuations look like at early times. We can also check for higher order correlations. And so the first deviation from a Gaussian power spectrum would be the 3-point correlation function. And that's found to be small. So if you take an appropriate ratio of the 3-point correlation function of zeta divided by appropriate powers of the power spectrum, you get some measure of the amount of non-Gaussianity in the fluctuations. And roughly speaking, we're going to discuss this in a little bit more detail later, but roughly speaking, the amount of non-Gaussianity is limited to be less than 0.1%. Okay? And I'm going to qualify this a little bit because that's dependent on what type of shape this pi spectrum has. But for the basic scale invariant shapes of non-Gaussianity, this is the limit that we get. Another important feature of these perturbations are that they span very large scales. So superhorizon scales at the time when we measure them in the Hot Big Bang. And they're correlated and coherent on these large scales. Okay? So what that suggests is that these fluctuations weren't created causally during the Hot Big Bang, but somehow there had to be a pre-phase before the Hot Big Bang that generated these fluctuations. Okay? And one way in which we infer this is by looking at the correlation between the polarization of the microwave current and its temperature. And we find that it's coherent at very large scales. That coherence suggests that these fluctuations were created before the Hot Big Bang. And so inflation, of course, is precisely such a mechanism that operated before the Hot Big Bang. And it includes a very elegant mechanism using quantum mechanics to generate these observed correlations. And so here I'm defining inflation in very general terms, purely kinematically. So for me, inflation at this point is just a phase in the early universe where the Hubble expansion, h of t, was nearly constant. Okay? Therefore, sources an expansion that is nearly exponential in time. Okay? That's a purely kinematic statement, the minimal assumption I have to make about the early universe in order to solve the horizon and flatness problems. But importantly, I didn't have to assume at this stage what the precise mechanism of inflation was, whether there was a fundamental scalar field driving the expansion or something else. This is simply a kinematic statement about the expansion of the universe at that time. So to analyze these fluctuations during inflation, it's first of all important to identify what the massless degrees of freedom were during inflation. Okay? So let's first discuss what's the minimal set of massless degrees of freedom that we can have during inflation, and try to see if that minimal set of fluctuations is sufficient to explain these observed correlations. So one massless degree of freedom during inflation, of course, is the graviton. And so we're going to talk about tensor mode fluctuations later. But there's a second massless degree of freedom that is guaranteed to be there as soon as you say the words nearly constant Hubble rate expansion. Okay? And that's the degree of freedom associated with the local time shift, the time delay or time advancement of this inflationary history. Okay? So far I've defined inflation in terms of a history h of t. I can now locally perturb that history by a function pi. And this function pi has various names. Okay? So I can call this, some people call this function pi the adiabatic mode. Because if after inflation during reheating I couple this field with standard model degrees of freedom, it will generate so-called adiabatic fluctuations. So these are fluctuations that don't distinguish between the different components. So there will be no fluctuations in the different composition of the universe. So the fluctuations in all of the species will be synchronized and all determined by the single degree of freedom pi. So to emphasize that, sometimes this is called the adiabatic mode. Some people call this the Goldstone boson of broken time translations. Okay? since you see that this mode is only generated because there's some time evolution during inflation. And so this is a breaking of the zeta time translation symmetry that can be parameterized in terms of this local degree freedom. And then colloquially sometimes this field is just called the clock because it's a field that measures time for a local observer. So in a local patch, different observer measures slightly different physical times, and that's parameterized by this perturbation pi. Okay? So what's nice about this field pi is that it's guaranteed, by a generalization of Goldstone's theorem, it's guaranteed to be massless or very light during inflation. So in the simplest scenario, we can look at quantum fluctuations of this field pi, and it turns out that these quantum fluctuations in the field pi are directly related to the field zeta that I introduced earlier, just by rescaling by the Hubble rate. And during inflation, the Hubble rate is nearly constant, so these are just literally proportional to each other. So if you wish, you can think of pi and zeta as being equivalent, at least most of this talk. Okay? So this pi fluctuation directly sources zeta fluctuations. So we can ask the question, if you look at fluctuations in pi, will they give observed zeta correlations that look anything like what we've seen in the study? Of course, I wouldn't be telling the story if that wasn't the case. Okay. But the nice thing about this description is that it leads to a very model-insensitive description of the inflationary perturbations. It's a guaranteed massless degree of freedom, and we can look at fluctuations generated for this massless degree of freedom. And sometimes to emphasize the uniqueness of this kind of description, this is called the EFE of inflation. Rather modestly. But it's the unique degree of freedom that the first thing we should be looking at when we look for the source of fluctuations at credit times. So let me give you a quick sketch of how we describe the effective action for this field pi. So starting off, there's a universal term, there's a kinetic term for this field pi. Okay? And this kinetic term is normalized by the rate of change of the expansion. So I told you this field pi only gets generated when there's some time evolution. So you see in the limit where I go to perfect zeta space, so H dot will be vanishing in that case, this becomes a non-dynamical field. And it's only the breaking of the zeta symmetry, which is characterized by the rate of change of the Hubble rate, that induces a dynamical field pi. Okay? So at lowest order, we just get some massless free field for pi. And so most of you are probably more used to this language of writing things in terms of a fundamental scalar field for slow roll inflation. It's very simple to go from just a simple slow roll action here, expand the inflacon field in terms of this perturbed time coordinate. A leading order what you would get is simply a free massless field, okay? With a coefficient that sets by the rate of change of the field phi dot. Okay? So this leading term characterizes nothing but the leading dynamical behavior of the fluctuations in the inflacon. But then there can be higher derivative corrections to the inflacon, and those higher derivative corrections will be reflected by nonlinear corrections to this kinetic term for the field pi. Okay? And that's what I've shown here. So these are nonlinear corrections, but the fact that we're expanding around the given inflationary history, that symmetry constrains the type of terms that I can add here. So one thing you notice, for example, is that there's a relationship between a linear term and a quadratic term. So the symmetry is still non-linearly realized, and that has some consequences for the size of perturbations that we can generate in this framework. So let's ask what these additional terms can do to my fluctuations. So first of all, because Lorentz invariance is broken, these fluctuations pi don't have to propagate at the speed of light. So there can be a non-trivial dispersion characterized by sound speed for the fluctuations. And so that non-trivial dispersion has an effect on both the power spectrum and also on higher order correlations. So here I've actually shown you what the predicted power spectrum would be in this minimal case. So it has this at the top here, so let me just go through what the structure of this prediction for the power spectrum. So it depends on the Hubble rate during inflation, depends on the rate of change of the Hubble rate, and on the sound speed of these fluctuations. And so it's not so hard to understand the structure. Basically, any canonically normalized massless field during the zeta phase has fluctuations that grow as h squared. This is not a canonically normalized field because of this normalization here. So in order to canonically normalize the field, I have to take account of this prefactor. This is also not yet the zeta fluctuation because pi and zeta were related by a factor of h. So there are two extra powers of h on the top, just by going from pi to zeta. And for small sound speed, the fluctuations are in fact enhanced, and so this power spectrum for zeta fluctuations will scale inversely of the sound speed. Okay? So you can understand all of these factors, but the important point to note here is that this predicted power spectrum depends on a combination of three different parameters. So we have measured the size of this power spectrum, but that doesn't tell us anything individually about each of these parameters. It just tells us about this particular combination of h, h dot, and sound speed. As I already mentioned, this action here is constrained by symmetry. In particular, there's this nonlinearly realized symmetry that relates different powers in the perturbation expansion. So that means that a small sound speed, which affects the dispersion of the quadratic action, also affects higher order terms. So in particular, for small sound speed, I have a unique cubic interaction that gets enhanced. So I can't make the sound speed small without generating nonlinear vertices and generating several numbers of non-Gaussianity. So this non-Gaussianity parameter that I introduced earlier will scale inversely as the sound speed squared. And that means the fact that we haven't seen non-Gaussianity will limit the smallness of the sound speed fluctuations. And actually, I should have said that at this level, leading order derivatives are in fact two independent cubic operators. One that is fixed purely in terms of the sound speed, and a second one that has a second free coefficient, which I've labeled A here. So we can look at a two-dimensional exclusion plot, which puts observational constraints on the size of the sound speed and the size of the second coefficient A. These shaded regions here are the regions that are still allowed by the data. So of course, slow roll inflation is still allowed, and some deviation from slow roll inflation is still allowed. But as soon as I make the sound speed too small, I would generate large amounts of Gaussianity that's not consistent with the observed Gaussianity of the CMB fluctuations. And so in particular, if I marginalize over this second parameter A, I get a lower bound on the sound speed, which is telling us that the sound speed has to be bigger than about 0.02. Okay. And we're going to see in a moment whether that's a weak or a strong constraint. Okay. That's some deviation from the kind of canonical slow roll picture that's still allowed, but it's limited to be bigger than about 10 to the minus 2. Okay, so that's the first massless degree of freedom, which solves the density fluctuations. The second massless degree of freedom is a graviton, which solves its tensor mode fluctuations. The action for the graviton is even more constrained by symmetries, and so there's not so many things I can do to the action for the graviton. In particular, the kinetic term of the graviton is normalized just by the Planck mass. And so therefore, the power spectrum of graviton fluctuations, it's almost canonically normalized, so it just scales with the Hubble rate squared, with a rescaling given this by this Planck mass normalization. And that's why the power spectrum for tensor fluctuation is simply given by the ratio of the Hubble scale to the Planck mass. Okay? So if we were able to observe tensor mode fluctuations, it would immediately tell us the size of the Hubble scale in units of the Planck mass. Okay. Usually these observational constraints on the tensor power spectrum are expressed in terms of the tensor to scalar ratio, little r, because we have measured the power spectrum for the scalars. We know this is a 10 to the minus 10 normalization, so we can get some, we can take the ratio and express our constraints on the tensor component in terms of this tensor to scalar ratio. So here I've shown you updated constraints on this parameter r. So these are measurements that were released in last November, I believe. The Keck array and the bicep. So this tensor to scalar ratio R is now limited to be less than 7%. Okay, so that's the latest update on this important parameter. And we can see that this is now reaching interesting levels of parameter space where the simplest kind of things like m squared phi squared are definitively excluded by these type of measurements. Okay? So you can see these contours here, contours in the R and S plane. The allowed contours here are these loop contours, and m squared phi squared has a prediction that lies here, which is safely outside of the regime that's still. Okay, so it's useful, I think, in order to get some more intuition for what the predictions are for this fluctuation spectrum, to think about the basic energy scales in the problem. Okay? I just want to do a quick exercise of going through the basic energy scales and seeing what we know about the basic energy scales here in inflation. As I already said, the fundamental energy scale that we have is the hover rate. Okay? This hover rate, in some sense, sets the energy scale of our experiment. So fluctuations are frozen when they cross the horizon, which is when the frequency of a mode matches the hover rate. So since we typically trace these fluctuations back to the moment of horizon crossing, when we make measurements in the CMP and we want to relate them to inflation, this is the energy scale that we're measuring by making that transfer. And as I said, we don't really know what this Hubble scale is yet. We have a lower bound because we haven't observed denser mode fluctuations. So we know that the Hubble rate has to be a factor of 10 to the minus 4 times smaller than the black mass. But we don't know whether it's much smaller than that or whether it's just around the corner, and we might be able to see tomorrow. A second fundamental scale is the scale of symmetry breaking. So that's the rate of change of the inflation in the background. During slow roll inflation, this is simply given by the inflow of speed. Okay. But more generally, if you don't want to commit yourself to a slow roll model, it's simply given by the rate of change of the Hubble rate, h dot. Okay. And so in order to keep things general, I'm going to call this scale of symmetry breaking f pi. So below the scale f pi, it's useful to think of these fluctuations as boson fluctuations, while above the scale f pi, you have to integrate in the background, and new degrees of freedom are guaranteed to become relevant. And you notice that the scale h here is below the scale f pi, so at horizon crossing, it's very useful to think of these fluctuations as boson modes. In particular, we actually know the hierarchy between h and f pi. Okay? This is a measured quantity. So it turns out that the power spectrum of curvature perturbations can be expressed precisely, and this is a very general relation, it doesn't assume slow roll or anything like that, can be expressed precisely in terms of the ratio between h and f pi. So by having measured the size of this, we actually know what this hierarchy is. And so this hierarchy is 58. So we know f pi has to be bigger than h by a factor of 58. Okay. So in the event that there are strong self-interactions of this lodestone, there's an additional scale that denotes the strong coupling of these fluctuations. So these fluctuations are guaranteed by the Gaussianity of the CMB to be weakly coupled at horizon crossing. But as we extrapolate to higher energies or higher frequencies, there might come a point where the theory becomes strongly coupled. So call this point the scale lambda. And actually at the moment we don't know whether the scale lambda appears below or above the scale of symmetry breaking. So in particular, we don't know whether the theory has to be recompleted before these new degrees of freedom associated with the background are guaranteed to play an important role, or after that. Okay? In fact, all that we know is the non-Gaussianity parameter itself is related to the ratio of h over lambda. That's constrained to be less than 10 to the minus 3. And so then putting in order 1 factors, you find that the scale lambda has to be bigger than 5 times the whole scale. Okay. But importantly, it's not yet bigger than 58. So it's not yet constrained to be bigger than this symmetry breaking scale. So what I've told you so far is just the fundamental energy scales of inflation as described from the bottom up. So just the minimum amount of information that we have gained just by looking at the data and not trying to impose any theoretical bias or much theoretical bias on trying to explain these fluctuations. But of course, ultimately, we hope to be able to embed this kind of framework into a more unique complete theory and try to answer questions of what actually generated inflation. And we have a strong suspicion that when we do this, there will be additional energy scales that become relevant. So in string theory, in fact, we have a very good, we know what these scales mean. So there will be the string scale and the Kaluza-Klein scale, maybe the scales of superpartners if the dynamics during inflation was at some sort of symmetric origin. And so we expect these scales to become relevant. In fact, we expect these scales to become relevant before the time scale. Okay? So especially in the string theory context, there will be additional UV scales that will enter the problem. And so it's interesting to ask, first of all, if we can see any imprints of this, and how close these scales are relative to the Hubble scale and the Planck scale. Okay. And what's exciting or interesting about inflation is the fact that it's very sensitive to these scales. Okay. So we usually have hard times to decouple all of these energy scales, and that's a blessing and a curse. It's a curse because it makes it hard to control the inflationary dynamics without having a complete understanding of all of these effects. But it's also a blessing in the sense that we might be able to use inflation as a way of exciting these these degree of freedom and learn something about these scales, which we usually have a hard time accessing. Okay, so I just want to emphasize that there are actually two ways in which inflation is sensitive to higher scale physics. The first way is, of course, famous in the sense that the inflationary background is sensitive to Planck suppressed directions. So we're sensitive to making assumptions or corrections suppressed by the Planck scale, even for describing the inflationary background dynamics. So whether inflation occurs or not, or how long inflation lasts, will be sensitive to operators that we can define at the Planck scale. And that has been covered by many speakers at previous strengths conferences. So in particular, I would advertise these two talks. So I'm going to spend less time, in fact, on this more famous UV sensitivity. And so instead, I want to emphasize also the second aspect of UV sensitivity, that inflationary perturbations, so the perturbations that we observe, can be sensitive to massive particles, or these high-scale degrees of freedom. And that also has become really more increasingly people have tried to study these things. So this is not as general as expressed UV sensitivity, but it has an added benefit that it potentially leads to observable effects directly imprinted into our observables. And so it's exciting to still discuss this in a little bit more detail. And I should say that one of the first papers to analyze the phenomenology of the effects of massive particles on inflationary perturbations was by Xingyang Chen and Yi Wang. Yi is here today, so you can ask him about this also. And then there were a lot of people who refined the basic picture that Yi and Xingyang had introduced. And also there were some talks at recent string conferences that describe this. And in fact, Nima gave a very nice set of Hazi lectures that I enjoyed, so you can also check this out there. So what I will do in the rest of the talk is to describe two particular examples in how massive fields can impact cosmological observers. So I want to discuss the effects of massive fields, high-scale degrees of freedom, on the non-Gaussianity of the fluctuations, and on tensor modes. And for the tensor modes, I'm going to be describing effects both on the power spectrum and more futuristically also on the tensor non-Gaussianity. Okay. So let me start off describing non-Gaussianity. So first of all, it's important to appreciate that there's an infinite number of ways, of course, in which a distribution can be non-Gaussian, but only one way for a distribution to be Gaussian. And so if it's Gaussian, everything is described in terms of the power spectrum. And so the description that I've given so far in terms of a power spectrum of CMB fluctuations is complete. Okay. And what's useful for this purpose, although there's an infinite number of ways in which the universe could be non-Gaussian, the data already suggests that it's not an arbitrary deviation from a Gaussian spectrum, but some small deviation from a Gaussian spectrum. And so we can describe the data to a good approximation as Gaussian with small perturbations. Okay? So that's what we're going to be doing. And so then the first diagnostic of non-Gaussianity is to look for higher point correlation functions that lead to small deviations from this Gaussian PDF. And so the first diagnostic is the bispectrum, so a 3-point correlation function in real space. Or in Fourier space, it's the correlation between 3 different Fourier momenta. By the homogeneity of the universe, this correlation function is constrained to conserve momentum. So there's an overall momentum conserving delta function here. And then there's a shape of this bispectrum that's given by this function. Okay. So first of all, I've already introduced this earlier. The amplitude of the bispectrum is defined in terms of this parameter, which is taking this bispectrum shape function, evaluating it in the equilateral configuration, where the 3 different wave numbers have equal size, and dividing it by appropriate powers of the power spectrum. That gives me a number that allows me to measure the size of the Gaussianity. So let's try to put this number into context. You know, what's a big and a small number for this value of f and l? So first of all, in my mind, so the theoretically interesting regime of non-Gaussianity spans about 7 orders of magnitude. Okay? So at the high end, when this parameter here becomes 1, the theory becomes completely non-perturbative and non-Gaussian. Okay? It's not a small deviation from a Gaussian spectrum anymore. So we already know this is kind of what we, just from the fact that we looked at the sky and the first approximation it looked Gaussian, we don't think we have to go into the regime where it's completely non-perturbative and non-Gaussian to start with. So we cut off this parameter at this upper end here. And then at this lower level, at the level of 10 to the minus 7, we would generate non-Gaussianity just by gravitational evolution. So if you imagine you start off with a purely Gaussian spectrum, and then the spectrum evolves non-linearly to the Einstein equations, for example, you would generate this amount of non-Gaussianity just by that evolution. Okay? So in canonical slow roll inflation, for example, this is roughly speaking how the non-Gaussianity gets generated at the level of 10 to the minus 7. Okay? So below that level, it's possible that we could tease out this small levels of non-Gaussianity, but it becomes very challenging, and it would be polluted by all kinds of non-linear gravitational effects. So it's more interesting to look for deviations that are stronger than the gravitational, which would live in this regime here. If you then look at the CMB data, it rules out the top 3 orders of magnitude in this range, and with the qualifier that this depends on the shape of non-Gaussianity. And there can be certain shapes of non-Gaussianity, like the things that I think Igor is going to be talking about often, that in fact are not constrained in this type of parameterization as much. Okay. But if the fluctuations are scale invariant, and maybe the higher point correlation functions are scale invariant, then roughly speaking this type of parameterization applies. So we have ruled out 3 orders of magnitude, but we're leaving a window of opportunity, as I like to call it, of about 4 orders of magnitude. Okay? And so the type of effects that we'll be discussing are hoping to find signatures of heavy fields within these 4 orders of magnitude in this parameter. Okay? So that's the amplitude of the non-Gaussianity, but a lot of information is contained, or arguably even more information is contained in the fact that this bispectrum has momentum dependence. So we have 3 momenta, and we can vary these 3 momenta subject to a triangle inequality. So they have to form a closed triangle. So there's special triangles like an equilateral triangle or a very squeezed triangle, or triangle with flat edges. And then everything in between those special possibilities. So I want to focus on 2 types of triangles. So this is, and we can classify the shape of non-Gaussianity by the dominant signal. So whether the signal has dominant support for equilateral triangles or dominant support for squeezed triangles. And I'd like to argue that the massive particles can have 2 types of effects, which are sometimes called virtual effects. Heavy particles that can be integrated out and lead to self interactions, local self interactions in the intercon field. That typically leads to signatures in this equilateral limit. And then real particles that I can produce on shell just by the expansion of the universe, which leads to effects in this squeeze momentum configuration. And I'm mostly going to focus on this, but these type of constraints on the fluctuations pi that I introduced earlier were in fact constraints on the virtual effects. So just to make this distinction between virtual and real a little bit more precise. So virtual particles are particles that are much heavier than the Hubble scale. So these can therefore be integrated out during inflation. They then lead to local interactions of the intercon fluctuations. And these local interactions will be reflected in analytic scalings of this correlation function. In particular, analytic scalings as I go to soft momentum limits. I take the soft momentum limit of this bispectrum, I go to the squeeze limit. I expect the correlation function to become analytic in the ratio of the soft and the hard momentum, and that's a signature of local interactions. In contrast, real particles have masses that are close to the Hubble scale or below the Hubble scale, so they can't be fully integrated out, but they can be produced due to just the expansion during inflation. In terms of the low energy degrees of freedom, such as pi, they will be reflected by non-local interactions. And those non-local interactions will show up as non-analytic scalings in the soft momentum. So for the rest of this part of the talk, I'm going to be focusing on this second situation, where there's a spectrum of particles with masses not too much bigger than the Hubble scale, so that they can be accessed directly and produced on shell during inflation. And there are several possibilities for this type of situation that I've tried to sketch here. So either you can have a set of masses that are very light, so they have masses much less than the Hubble scale. So these are the set of particles described here. And then we have another very light degree of freedom, which is this Goldstone mode. And then these fields can interact with the Goldstone mode. This situation is very hard to make generic predictions about. Okay? Because now all of the fields are fluctuating wildly, and the curvature perturbation zeta is not just given by pi anymore, but it's given by the combination of all of those fields. Zeta itself is not necessarily frozen outside of the horizon, so it's hard to make a non-independent prediction of the final statistics of zeta fluctuations in this type of setting. Okay? Although a lot of people have studied this, but for the reason that one can't make specific predictions, I'd like to focus on two different situations. So there's a situation where the extra particles are not much lighter than the Hubble scale, but have masses right around the Hubble scale. And two rather natural situations where this could arise is if the underlying dynamics during inflation was supersymmetric, except for the spontaneous breaking of supersymmetry due to the vacuum energy during inflection. So in flat space, this theory might be supersymmetric, but then when you put that theory into an inflationary context, the inflationary vacuum energy will break supersymmetry, and that will induce masses to these extra fields that are, what are the Hubble scale or slightly below that Hubble scale. So that's a rather natural way of generating fields that have masses clustered around the Hubble scale. Another possibility would be if the fundamental origin of inflation was very stringy. Okay? If for some reason that we don't understand very well at the moment, when we understand the strong curvature regime of string theory and a time-dependent background better, we might find that inflation is an emergent consequence of this very complicated dynamics. So of course that's hard to analyze, and therefore there are not many examples of this. But one would hope that at the end of the day, when all of the dust settles, we could describe the phenomenology of such a scenario by a weakly coupled theory of inflaton particles coupled to degrees of freedom with masses according to the string scale, and maybe particles with spin corresponding to higher string excitations. Okay? And then one could use the Hubble expansion of the universe to generate excitations of these higher scales. Okay? That's of course like a dream scenario that would be nice to make more precise, and it would be nice if some of you could give us some tools to really show that something like this can happen, and that the origin of inflation really had some more fundamental stringy origin. But then the mechanism that I'm going to be describing here is going to allow you to then actually really test this, to try and excite these string modes and look for their signatures. Okay, and then EVA, I'm not going to say too much about it, because EVA is going to be talk about this, I think. They have introduced an interesting scenario where these massive fields are coupled to the inflaton in such a way that they become sensitive not just to the Hubble scale as a source of generating particles, but even the time variation of the inflationary background leads to non-negative particle production. And so that gives you access to massive particles with even slightly higher masses than the Hubble scale. Okay? And so he was going to be describing how this works. Okay, but I want to describe how these type of scenarios work. So the idea is that if a field has mass according to the Hubble scale or less than the Hubble scale, you can spontaneously produce that field in an expanding space-time. Since these fields are massive, they can decay into light fields, or they have to decay into light fields, because otherwise at late times they will become completely gone and diluted. So in order to observe the effects, they have to decay. They will decay into, for example, inflaton particles. And if this decay is a nonlinear process, you can generate higher order correlations of the inflaton because they originated from a common source. Yeah? So there are two particles that we spontaneously produce. Each of these particles decays, for example, into two or more inflaton particles. And so at the final reheating surface, you can then have higher order correlations of the inflaton. So here, in fact, we have generated a 4-point correlation function. If I take one of the legs and evaluate it on the background inflaton and evaluate the remaining legs on the inflaton perturbation, or this perturbation pi, I would generate a 3-point correlation function. So this lowest order statistics that I introduced would be generated by such a process. And as Nima and Juan showed last year, this type of process leads to this characteristic non-locality in cosmological correlators, because this is generated by a decay of a massive particle at different moments in time and different places in space. So let me give you a concrete example for this. So this example is two scalar fields. One of the fields has a mass that's a few times the Hubble scale. And there's a cross coupling between this massive field and the infotone field. In this case, it's a dimension 5 operator, so that's got some scale lambda. I can try and integrate out this field because it's heavier than the Hubble scale. And so in fact, the leading effect would come from this integrating out of the field. And of course, as usual in integrating out massive fields, this will lead to an infinite series of local terms. That series can be understood as an expansion in the energy scale of the experiment, h, divided by the mass of the particle, m. Okay? There's a series of local terms that lead to analytic scalings in the correlation function with amplitudes given by some power of h over m. But in addition, we can have smaller effects that lead to non-local terms. So they're smaller, but they have some very characteristic signature with amplitudes that are proportional to some kind of Boltzmann suppression of the mass of the field to the Hubble scale. Okay, so as I already said, this non-locality shows up as non-analyticity in the squeeze momentum limit. The masses of these particles will lead to very distinctive oscillations in this squeeze limit. Okay? So here I've shown you what the squeeze limit looks like. So I'm taking one of the momenta of the fields to be soft. So k long is a soft momentum, and I'm taking to 0 to be much smaller than these two hard momenta. In that limit, this correlation function will oscillate, just because the massive field oscillates between these two times of particle decays. And so these oscillations of the massive field in time get imprinted into oscillations in momenta. If the particles have spin, like we're envisioning in this kind of very stringy parameterization of weakly coupled massive higher spin particles, that leads to a unique angular signature in this correlation function. So if I take this squeeze limit with a hard momentum Ks and a soft momentum Kl, and I vary the angle between the hard momentum and the soft momentum, I expect the signal to vary in a characteristic way that depends on the Rondel polynomial as a function of that angle, with a degree that depends on the spin of the particle. Okay? So both the mass and the spin of the particle get imprinted in particular signatures of this soft momentum correlator. So in principle, if we measure very accurately this soft momentum correlator, we could invert the problem and identify if there are additional particles present and measure their masses and measure their spins and so on. So okay, of course I should say something about the amplitude, this parameter FNL. So in general, this amplitude is very small. Okay? So in particular, if this mixing between the extra massive field and the interphone is purely mediated by gravitational interactions, so that this mediating scale lambda is given by the Planck scale, then there are two suppression factors, at least two suppression factors in this amplitude. There's first of all the slow roll parameter epsilon, which determines kind of the size of gravitational interactions during inflation. And then there's a Boltzmann suppression due to the fact that the heavier I make the particle, the harder it is to produce. Okay. So this is actually the size of the amplitude that we would be producing just by gravitation. This gravitational floor that I introduced earlier, dependent on 7, that's this epsilon level number asymmetry. And then this is further suppressed by the fact that massive particles are hard to produce during inflation. But that's of course under the very conservative assumption that the only force mediating between these two particles is gravity. In principle, there can be additional forces between the Planck scale and the Hubble scale. If those forces are present, you can in principle boost the signal by at least a factor of 10 to the 7. Okay? So that's a possibility, and in particular, it's a possibility discussed by Shinier and me. There's also the possibility of having specific time-dependent couplings to these particles. In that case, this Boltzmann suppression gets reduced to a suppression by a higher scale. And so Eva is going to be describing that leads also to a boosted type of signal, although the signal is a little bit different. If the masses are less than the Hubble scale, then there's in fact no Boltzmann suppression. There's also then no oscillations in this field because the field is not massive enough to oscillate, but there's still a characteristic non-analytic scaling in this squeeze limit. Okay, so this is just to summarize. If we were able to observe these non-analytic scalings in the squeeze limit, we would see their oscillating feature. This would measure the mass of the particle. If we see their angular dependence, we would measure the spin of the particle. And so, the hope is that by having stronger than gravitational interactions mediating between those two particles, you could have this show up in this window of opportunity. And future observations, just to show you what they look like. Future CMB basically has a hope of reducing these or improving these limits by one extra order of magnitude. Future large-scale structure with a lot of hard work may be able to reduce this further by another order of magnitude. And then the final 2 orders of magnitude, people are starting to speculate whether using the topography of centimeter fluctuations can close this final part of this window. But here the forecasting really depends on the optimism or pessimism of the researcher. Okay? So I'm happy to discuss what goes into there, but in principle, at least in terms of just the raw mode counting, 21 centimeter can be able to close this hole. Okay, so then in my final 10 minutes, I want to talk about tensor mode fluctuations a little bit. Here I just want to emphasize that there are 3 theoretical targets for tensor modes. So first of all, of course, there's the amplitude of the tensor modes. And so this amplitude probes the UV sensitivity of the inflationary background. And that's a famous story that I won't repeat. And then there are more subtle, harder to observe effects on the scale dependence of the tensor fluctuations. And more futuristically, maybe even the non-Gaussianity of the tensor. And those 2 observables are sensitive to in exactly the same way that, or in a similar way to the described for the scalar fluctuations, are sensitive to the UV through the effect on the inflationary fluctuations. So in fact, in the view of time, I have some comments that are rather standard about how the tensor mode amplitude probes the UV through the famous Planckian excursion that it requires of an inflaton field. And so I'll leave this in my slides. You can read this in your own time, but it's nothing very. The story has been told enough times. So what I want to instead discuss is the question: if we were to observe tensor modes tomorrow, and I want to emphasize that we might literally observe this tomorrow, or people might already have observed this. In fact, later I'm going to have a slide showing you that there are about 20 or 30 experiments actively looking for tensor mode fluctuations right now. Either one of these experiments could see something. So the question I want to pose is, if one of these experiments came out tomorrow and told us that tensor modes were present at a rather large level, what can we learn? Or what additional physics could we probe from these measurements? And so I'm going to discuss 2 rather futuristic examples. But again, they are examples that are of primary interest to string theorists. So of course, one of the generic consequences of string theory is that there are higher curvature corrections for Einstein gravity. These curvature corrections are organized by the string scale. And so just like before, if we had a scenario where the string scale was sufficiently low relative to the Hubble scale, we might hope that we will be able to see these characteristic effects. Of course, this is at the limit of control of an effective field theory. So it's important that we're able to phrase predictions in this regime that are protected by symmetry principles. Okay, and so that as was shown in these papers, that's possible by appealing to a weakly broken conformal symmetry during the inflationary era and using information of this underlying conformal symmetry to make predictions for the cosmological correlators that are insensitive to the details of kind of a Lagrangian formulation of this theory. So I just want to highlight 2 effects. One effect that these higher corrections can have on the 2-point correlation function. So the leading correction that you can have at the quadratic level of the action of tensors is that the Einstein-Hilbert action can be corrected by a Weil squared term, okay, with a coefficient that might be inflaton dependent. And the reason, the various ways of writing this correction, but the reason I've written in terms of the Weil tensor is because the Weil tensor vanishes in an FLW background. So it starts at linear order in fluctuations. And so we will be able to put it into this form by using kind of the background equations of motions and using theory definitions and so on. So this is analyzed by one paper in 2008. The leading effect that this type of correction has is that it changes the sound speed for the tensor fluctuations, and it changes it in an inflaton dependent way. So as the inflaton evolves, the sound speed will evolve in time So the power spectrum for the tensor mode fluctuations will be also time dependent. And so this means that we inherit kind of a change to the scale dependence of the tensor mode fluctuations. And so that's what I've indicated here. The tilt of the tensor spectrum has a standard form in Einstein gravity, just given by this lower parameter epsilon. But in the presence of this higher curvature correction, you might get a change to this tilt of the spectrum. So if we are able to observe the tensor mode spectrum, observe very carefully the tilt of the spectrum, and find it not to satisfy a consistent relation between the size of the tensors and their amplitude variation, that might be an indication for some kind of correction to gravitational action. The second possibility is that this violet tensor leads to a correction to the cubic action. Okay? And in fact, Malsina and Pimentel showed that in fact this correction is unique. The two parity conserving corrections that one can have to the cubic Lagrangian. So that also means that the 3-point vertex or the graviton 3-point function gets two unique contributions. One that can be associated with Einstein gravity, one that can be associated with higher curvature correction. So if we were able to observe the 3-point correlation function of this graviton and found it not to correspond precisely to the Einstein gravity result, this has to be an indication of this relationship. Okay? And now observing this in fact would be very interesting because this Weyl cube correction has been argued to violate causality unless the theory, this Weyl cube term is embedded into a UV completion that contains an infinite power of spin particles. Okay? And of course, we take an infinite power of weakly coupled massive spin particles almost as a definition of symmetry. Okay, so this is the slide, in fact, that I was mentioning earlier. These measurements of V-mode polarization of tensors are really only beginning. There's a large number, this is not even a complete list, a large number of experiments that are taking data right now. And we look forward to hearing results from all of them. At the moment, BISEP and Thackeray are kind of an order of magnitude ahead of the rest of the field. But all of these other competing experiments are catching up. And they're bound to reach levels of sensitivity that we're looking for high energy theories. Okay, so then in my remaining few minutes, I just want to give you a very quick outline, outlook for future observations. And I want to go back to this inverse problem that I mentioned at the very beginning. So the measurements of CNV anisotropes have provided very precise constraints on the spectrum of primordial perturbations. So we have been very successful at taking CNV fluctuations and tracing back the origin to the beginning of the whole Big Bang. However, at present, these initial conditions are described extremely well by just two numbers. Okay? So we just need an amplitude and a slight scale dependence for these fluctuations, and that seems to describe all of the data that we have at the moment. So it's very hard just from those two numbers to extract, more detailed physics about the microscopic origin of inflation, and that's why I was describing a couple of scenarios where you can look for deviations from this scaling power spectrum in the non-Gaussianity or in tensor modes to tease out a little bit more information about what macrophysical origin inflation has. So this is just repeating this. In order to make progress, we really need theoretical predictions for deviations from these simple initial conditions. And so I've given two examples, but this, by no means will this example to me be representative or complete. In fact, it's hoped that future theorists or some of you will provide their own examples with their own motivations and their own observational signatures that we can look for. And what makes all of this exciting is the fact that there will be so many data sets available in the future to provide very stringent tests for any ideas that you might have. Thank you. Any questions?
Is it on? Hi, Daniel. Thanks for a very nice review. I just wanted to point out one thing, which is even as you said, in a situation where, say, the Hubble scale is or the string scale or so, we lack the tools at the moment to compute if there is such a viable scenario, the spectrum of perturbations. But I just wanted to say that we can still use the approximate conformal invariance, etc., of the Sitter space to actually put interesting constraints on the rough magnitude of the non-Gaussianity. And using the kind of ordered entities and so on, one can say that it's constrained by the observed tilt as well as the overall magnitude of the two-point function to be roughly in the range which we see it to be today. So you can still say something's using symmetries even where you...
Very good. Yeah, if I didn't have to rush at the end, I would emphasize it a bit more. Well, I do emphasize to people that they should look at your paper and the other paper. But make this point very clear.
Hi.
Yeah.
Good question. So you discussed the constraint on the hierarchy of scales from the top down relative to the Hubble scale.
Yeah.
Is there any constraint on those top down scales relative to the scale of time translation symmetry breaking?
You mean the UV scales now? Because I just the only
Yes.
Yeah. I don't think so. I don't think so. Yeah.
I was just wondering if you have any comments on the attempts in the recent literature by, say, Marshall and others to interpret the simplicity of the results in the data, still in terms of many, many fields, and sort of the central limit there causing them to nonetheless converge on various power spectrum. There seems to be a debate in the literature about this. Do you have any comments on it?
Yeah, there's a bit in the literature, I think, because what they're considering is many light fields with random interactions between those fields, and the question is whether the emergent power spectrum that you get for zeta fluctuations takes this very simple form, not because there's just one degree of freedom within the scalar dynamics, but because this collective dynamics is very complicated. Emerging from in large n, you get this. I think the tricky bit there is that you're not guaranteed to hit an adiabatic attractor for the curvature perturbation. So in principle, if you just randomly stick in many, many light fields with random interactions, the curvature perturbations will evolve outside of the horizon. And so I have to trace, in fact, and then if that non-adiabatic evolution is still present during reheating, I didn't become sensitive to the details of the reheating physics. Okay? So one has to, in those scenarios, in order to make predictions that I can trust tracing them through reheating, I think you have to funnel the fluctuations into a regime where only zeta survives and all of those heavy fields somehow we can access towards the end. I'm interested in the question whether it's possible to have emergent scale invariance from kind of large n behavior of many random fields. So far I've hit this non-adiabatic wall.